Well, this is mainly based on this paper here, which is just out. And so, okay, so this is a summary of what we're going to give you here. We've got a deep exposure in the EUV with the UVIS instrument, and we extract the plasma structure, the state of the plasma. And it turns out that it's primarily long-lived ions from Io, so it's hard to extract the input from Europa. Then the next thing we look at is the atmosphere, and disagree with the interpretation as an O2 atmosphere. It really has to be an atomic oxygen atmosphere at a density that's about 2 orders of magnitude lower. And looking at Voyager and Galileo results in the in situ measurements, results here are consistent with the Cassini flyby. And we don't find evidence for H2O as a source in what we're looking at. That is H2O in an atmospheric state. And conclusion here is that Io is the primary driver for what's going on. So this is the viewing geometry. The plasma sheet is about 3 RJ across, and so we integrate along here with the slit pixels, and out here gives us a background. So this is the spectrum, 148 hours of exposure. Everything in here is sulfur and oxygen ions. And the background here is at the ends of the slit. And you've got atomic hydrogen and helium. There's some residual oxygen ion emission there. So you see that there is no change in intensity from on and off the plasma, so we have no detection of hydrogen here. This is a normalization of Europa against the Io plasma torus, and everything lines up except for this feature here, which we never model. But, you know, it's going to be oxygen, probably ions. And so the difference is temperature between these two spectra. So this is the Europa plasma sheet against the model, and again, the model doesn't pick up these features in here. And here's the Io torus and the fit to the torus. The blue line is the data, and the red line is the model, the total model. The light green is the sulfur 4 component, so it's a good fit. And that's a 75,000 degree plasma. So here is a comparison of what we derive from that data. This is the Io torus at the eastern ANSA distribution. Total electrons 1418 compared to 96 in the Europa plasma. Temperatures 250,000 degrees here, 75,000 degrees. As the plasma drifts outward, you build ion charge going outward, if you look at those ratios. Let's ignore this, except to say that you've got a lot of radiant energy coming out of the torus. Down here are rates. This is what Io has to put into the system, in a scale of 10 to the 25 atoms per second, 700. To keep Europa going, less than 5 on that scale. This is a column for Enceladus, very different because it's a weakly ionized plasma, but it's a good thing to compare to. Neutrals are not measured here. Neutrals are 2800. And the rate that Enceladus is dumping atoms in is 1500. It's more than Io. All right, so what we have here is that it's a low density plasma at Europa. Don't measure neutrals. We really can't tolerate neutrals in that system at any density greater than about 3 per cc. Electron densities are consistent with what we see at Voyager and Galileo. Temperature is the same within error in that plasma sheet, 250,000 degrees. And so it's in basic agreement with Russell's review in 2005 that Io is a driver for everything that's going on. So this is the atmospheric spectrum in the FUV. And so we have the 1356 line here of atomic oxygen and 1304. And in this spectrum, the 1304 line is optically thick with this 5 times 10 to the 12 per square centimeter. This is a optically thin calculation for E plus O. And this is the model fit here, the black line. The red line is the data. So we've got a 90,000 degree electron population and an electron density in that calculation of 14,000. So this is a compilation of the measurements from 1994. The Hall is in blue. The UVIS result is in green. And Roth is in red. The triangles are the 1356 transition. So everything is clustered around about 60 Rayleighs in all of these measurements, plus or minus 30. So you don't see a spectacular variation in any of these results. So looking at the ratios which determine whether you've got O2 or O, from E plus O2 at 90,000 degrees, you've got this solid black line across here. The ratio is above 3. If you lower the temperature, the ratio goes up. This is the optically thin ratio for E plus O. So the observed ratios all fall in between, right? But not very much above 2 here. And so the conclusion on that is that you have the atomic thickness here, the optical thickness here is about 1 for the UVIS analysis. So you're looking at a tau of 1 to 2 in these results. This is the search for Lyman alpha. Let's ignore this. We don't have time. No detection of Lyman alpha. So we don't detect Lyman alpha, we don't detect Lyman beta. So that sets a limit. And this is the model calculation for H2 in the atmosphere and in the plasma sheet. The red one is the plasma sheet. And again, I'm using Smith and Marconi as a reference here, and we're consistently 2 orders of magnitude below Smith and Marconi. And they're assuming an H2O, starting out with an H2O atmosphere. So there we are. We've got 1 to 2 times 10 to the 5 atomic oxygens at the surface in this analysis, and 10 to the 4 O plus comes primarily from Cleora, but we're in basic agreement with that in terms of upper limit on the O plus emission. So it's a fairly significant plasma at the surface. The ratio here, ion to neutral, is about 0.1. We don't see anything of the production that Smith and Marconi would come up with, and again, we're in agreement with the Voyager and Galileo results. So here is an issue. With the Roth results, I have no reason to disagree with what they've got, but want to point out some issues that have to be addressed here. They infer, based on Lyman alpha observations, they infer 10 to the 32 H2O molecules in those plumes that were seen in the south region. The dissociation rate into H plus OH, then, on that basis, is about 10 to the 28 per second. The hydrogen product goes out into orbit around the system with Europa. The OH product stays in the atmosphere. The problem that arises there is that it takes 100 seconds to replace that atmosphere with the rate coming off. And so the question is, well, why wasn't the disk average at the time of the plumes any different from the earlier measurements? So that's something of a worry. And the problem is we only have 10 to the 30 atoms in that atmosphere. 100 seconds to replace it with this plume. But the problem there is we don't know what the atmospheric recycle time is. We don't know what the physical chemistry of OH and O on the surface is. We really don't know anything about the microstructure of that surface in terms of, atomic rates. So, without a question, we need atmospheric observations, more of them, and we need more modeling. Roth et al. Is critically important. The only other issue that we addressed here was ion sputtering, and we're suggesting that what's happening here is that we're building charge on sulfur and oxygen as sputtering agents, and when you have a highly charged ion coming down on a surface, it's much more effective at sputtering. And has a tendency to give neutrals coming off. Neutral atoms, I should say, coming off. So that's it.
Okay, thank you. So Europa gets more and more interesting. We have time for a couple quick questions.
So we will be posting soon on AstroPH a rebuttal paper detailing numerous major errors and weaknesses found in the Shemansky et al. Work. The current list of co-authors on the rebuttal in alphabetical order is Fran Bagenal, Tim Cassidy, Peter Delamere, Bob Johnson, Barry Mock, Melissa McGrath, Kurt Rutherford, Lawrence Roth, Joachim Sauer, Andrew Steffel, and Daryl Strobel. So we encourage everyone who's interested in this to read the Shemansky et al. Paper, read the rebuttal, and draw your own conclusions.
Does anyone have a question? Is there a question?
I'll give you an example. We think that the plasma state determined is completely wrong at both Io and Europa, and that's just one of many things we think are completely wrong.
Well, I find that really interesting.
Okay, does anyone have a question? Yes.
You stated that for the H2 limitations that you're 2 orders of magnitude below Smith and Marconi.
Yeah.
Where are you relative to the H2 concentrations that are actually inferred from observations?
Are there H2 concentrations inferred from observations?
Well, Pontus gave them in the previous.
Oh, you're talking about the ENA result.
The lag observations would give the same results.
Yeah, yeah. I'm based on the previous paper. I'm not sure. I'll have to look at that to see how far that goes. But the earlier mock result, which was, I think, talking about 50 per cubic centimeter at Europa. The path length. Okay. Yeah. And that was about 10 to the 12? Yeah. Okay.
Okay, well, we better move it along now.
Yeah.
Okay, thanks, Don.